Basically, here we want to talk about Nielsen theorem, majorization. So let's suppose you have those four examples. This. If you check about them, you know by Nielsen theorem that normally you need to have the sum of them to be each of the time. How to say it? Uh, you need them to respect a certain order, like sum of e of x of xi. Some should be inferred to the sum of I of x of yi if x is represent c. And so basically, like here, for example, we have like square root of 0.4 is inferred to square root of 0.5. But the problem is that if you after you do the sum, so you have square root of 0.4 plus square root of 0.4, and here we have like square root of 0.5 plus square root of 0 of this. And so basically this is false, and so you don't have you cannot apply directly the majorization that we want, like um, so yeah. And that's it. Like there is really nothing else to to think about. Like maybe you can just remark that the more your state is entangled, the more there is chaos into it, and the more it can be at the bottom of the scale. While the quantum state that is not entangled, like majorize everything. So yeah, here there is no majorization, but what you can do in this type of case, you can just take a catalyzer that will permit you to make um, it happen. So yeah, um, yeah. If you take this and you multiply like this by this and this by this and do the majorization trick, like you'll see there will be no problem. So basically, like for example, like if we do this, like for CV, we'll got 0.24, uh, um, 0.16, and 0.24, and 0.16, and 0.6, 0.4, 0.6, 0.4. And so if you do the same for the second one, so you do like this letter V, it gives you 0.30, 0, 0.30, and after you have 0.50, 20, um, 1 over 4 multiplied by 6, like just 6 over 4. So you'll just get how many does it make? In because like it's like by 10 to 150 divided by to 125, and it's 25, it's 0.15, and so after you multiply by this it gives you 0.1, and after uh, you just get the same anyway. You get 0.15 and 0.1 or 10 as you want. And so when you have this, you can reordinate them both into crescent order. So um, let's call it like P for the first one and Q for the second one. P like it's just like so if we do the like 19, it's like 024, 024, 016, 016, 06, 06, 04, 04, and see if now we take this one, we call it like Q, Q just like 030, 020, 015, 015, 01, 01. And so if you do the addition, like first we have like we'll have like well, I think I can just suppress this to write what I want to write. We'll just have like 030 being superior to 024. We'll have after 050 superior to 048. And after you add 16, so it's like 64. So yeah, it's like 65 superior to 64. And after you have 0.80 superior to 64 plus 670, and right, no, it's 16 here. So yeah, it's like 15. After you add like 1, so it's like 0.9, and it's superior to 0.86, 0.80, 86, and yeah, because like here we need to put this now. And so after Um, we have this, and same second time, and so we're like we made this, and after we have like we have still 0.1, so it gives 1 0.80 90 12, and after and after um, we just have like 0 and 0. We can add 0 and 0 here because like here there is like um, how to say, we need to complete with two other elements. um, and yeah, so we just eliminated this, and so after we just put those two one, and so it just paid 1 0.96 and 1 0.11, and we already did all the stuff before, so we can put like 0 0, and so we just see that we respected the majorization in a way, and yeah, it's done. Like that we can see like the cumulative sum of p is infer equal to the one of q, so majorization is validated. The catalyzation has made a basculation of the inequality, like so the conversion by LOCC is now mathematically possible, and so we just verified it, and that's it. That's finished. Thanks.